Hi. Okay, hi, let's get started. I'm Hitesh Ballani. I'm from Microsoft Research in Cambridge in UK, and welcome to the session. It's the last session of the day, so let's keep the energy up, lots of questions, and in return, we'll take you on a lovely boat ride this afternoon or this evening. The session is titled Hardware and RDMA, and we have 4 excellent talks and 4 excellent speakers lined up for you. The first speaker is Daehyeok Kim. He's a PhD student at CMU. He does work on RDMA and programmable NIC hardware, and he'll tell us about a very cool way of using NIC-Offloading to accelerate multi-tenant storage systems. Over to you.
Thanks for the introduction. Hi, I'm Daehyeok Kim. I'm a PhD student at Carnegie Mellon. Today, I'll tell you how we can make replicated storage transactions faster by uploading them to the NICs. To give you some context of this work, many online services today rely on replicated storage systems. For instance, Azure Storage, Amazon S3, open source implementations such as RocksDB and MongoDB. To achieve high availability, integrity, and consistency, these systems use some form of replicated transactions. For instance, chain replication is a popular replication scheme used by these storage services. Notice that these storage systems are inherently multi-tenant, which means hundreds of replica instances can be co-located on the same server to improve resource utilization. However, we've seen that such replicated storage systems can suffer from large and unpredictable latencies. This result shows one such measurement, the latency of MongoDB in a multi-tenant setting running YCSB, which is a popular database benchmark workload. The x-axis is the number of tenants in a server, and y-axis the latency for running the workload. And the blue and red lines represent the average and tail latencies respectively. We see that as the number of tenants on a server grows, the average and tail latencies increase. Further, the gap between the tail and average grows quite rapidly. Naturally, such large and unpredictable latency can impact the end-to-end performance of storage-intensive applications. So, why does this happen? To understand this, it's useful to look at software and hardware stacks of these storage applications. Let us use chain replication as an example. Suppose there are 2 replicas and a front-end server in a replication group forming a chain. Assume that a front-end server wants to append the data to a log using logging operation. There are 2 typical steps each replica performs. First, when the replica software receives the operation along with the data, it first executes the operation. In logging, it will store the data to the storage. The next step is to forward the operation to the next replica in the chain. The same thing happens when processing other transactional operations such as locking and commit. So replica software performs the executing and forwarding steps with storage and network software stack, which are scheduled and run by CPUs. Also, when CPUs are busy, arbitrarily CPU scheduling latency can occur while processing incoming transaction requests, which can impact the replication latency. Indeed, in our experiment, we observed replica CPU utilization hits 100%. In multi-tenant case, since multiple replica instances are contending for limited CPU resource, this latency problem can become worse. So our goal is to improve the latency of replicated storage systems. Ideally, we want to remove the replica CPU from the critical path and offload the operations to the NIC and storage. To meet this goal, we present HyperLoop, a framework to enable fast replicated transactional storage systems. HyperLoop by itself is not a full end-to-end storage system, but rather it provides building blocks that developers can use to build such systems. In particular, we focus on chain replication as it's widely used today. There are three key ideas in our designs. First, we leverage the combination of two hardware technologies, RDMA and non-volatile memory, to enable the NIC to directly replicate data to durable storage. To overcome some practical challenges in realizing this idea, we leverage the programmability of commodity RDMA NICs and provide a set of new APIs that cover key transactional operations. Our research shows that HyperLoop can reduce tail latency for existing in-memory storage applications. On a practical note, realizing these benefits requires only minimal modifications for existing applications. For example, integrating HyperLoop into MongoDB requires 860 lines of modification out of about 500,000 lines of source code. Now, let me explain three key ideas in HyperLoop framework. To remove replica CPUs from critical path of chain application, we observed an opportunity to combine two hardware technologies, RDMA and NVM. RDMA allows us to access remote memory region through the network without involving remote CPUs. Now, NVM or non-volatile memory provides RDMA NICs with durable storage, so the NIC can directly write data to durable remote regions. However, just writing data to NVM via RDMA NIC is not enough for offloading replicated transactional operations from CPUs, as you will see. The first challenge is that replica CPUs are still involved to forward the operations to a group of replicas. Let me bring back the logging example to explain this. Here, logging operation can be replaced with RDMA write, since what logging does is writing data to log region in the memory. So, the NIC on replica can execute logging operation on behalf of replica CPU. However, replica CPUs still need to be involved to forward the operation. The second challenge is that existing RDMA primitives might be sufficient for data logging. They cannot perform other key transactional operations, such as commit or locking, which are required by most of storage systems today. Let me explain this problem using commit operation as an example. When the front-end server issues a commit operation, the data in the log region has to be copied to data region in the memory. However, since RDMA NICs does not natively support such a commit operation, the replica CPU needs to execute the commit operation as well as forward it, as mentioned previously. Similarly, executing other transactional operations such as locking also require the replica CPUs. So, can we address these challenges to let the NIC to execute and forward the transactional operations? In particular, is it possible to push the replication and transactional functionality of the replicas into the NIC? At first glance, it seems that we need to effectively put the software stack onto the NIC. That is, putting a full-fledged programmability in your RDMA NICs. Fortunately, we observed that there is a cool feature called RDMA wait that we can repurpose to make the replica's NIC to forward the operations without involving replica CPUs. Essentially, the wait operation allows the NIC to wait for a completion of a certain event, for instance, receiving event, and upon the completion of the event, it triggers the NIC to perform pre-programmed operations. While this set of operation is indeed limited we found that it is sufficient for our purpose. Next, I'll describe at high level how we can leverage this feature. Let us first look at the bootstrapping phase of our mechanism. Suppose there are two replicas, R1 and R2, and front-end server as shown in the figure. As soon as the replication group has been established, the HyperLoop library in the front-end server will collect the base addresses of memory region registered to the replica's NIC. The library will use this information in the data path as years later. And then the library on replicas program the NIC with RDMA weight and the template of target operation, for instance, write operation. This template contains the empty parameter value for the write operation. By using wait operation, the NIC will wait for a completion of a receiving event, and then it'll forward the programmed write operation. After the bootstrapping phase, the replica CPU do not need to be involved in the data path. Now, although the NIC can forward the data as soon as it detects the receiving event, we first need to set the parameter of the operation correctly without CPU. To do this, we designed a mechanism to enable front-end software to manipulate the parameter of write operation programmed on the replica's NIC. Let me bring back the previous example to explain how our idea works. To update the log, the front-end server issues a write operation to a first replica. And immediately after this, it will also send parameters for the write operation programmed on the NIC's, replica's NIC. And upon receiving this, the replica's NIC will update the parameter of the write, as shown in the figure, without involving CPUs. This receiving event will also trigger the NIC to forward the write operation with updated parameters. With this technique, the replica's NIC are now being able to forward the operation with proper parameters configured by front-end server without involving replica CPUs. Okay, then the only thing remaining is to making the NIC execute transactional operations. As mentioned earlier, existing RDMA primitives do not support some of key transactional operations such as commit and locking. Fortunately, we show by construction that it is indeed possible to abstract those transactional operations into memory operations. In particular, we can transform locking into memory write, commit into local memory copy, and locking into atomic compare and swap. Combining this memory abstraction with our operation forwarding mechanism, we designed HyperLoop primitives that execute transactional operations on a group of replicas. HyperLoop primitives consist of group lock, group commit, and group lock. Please refer to our paper for detailed design for each primitive. Now let me show you how a write operation in a typical storage system can be performed with HyperLoop primitives. The front-end server first updates the log using group lock. Then it tries to grab a lock, global lock, using group lock. If it grabs a lock successfully, it will commit the log using group commit. Then it will release the lock using group unlock primitive. So with HyperLoop primitive, the storage applications can perform transactional operations on a group of replica without involving their CPUs. To summarize, our main goal was to remove replica CPUs from the critical path of chain replicated storage transactions. We achieved this goal using 3 key ideas. First, we leveraged the combination of 2 hardware technologies, RDMA and NVM, to offload transactional operations from CPUs. And to solve some practical challenges, we show how limited programmability of RDMA NIC suffices to forward operations to group of replicas. And we provide UAPIs that cover key transactional operations. Developers can use our HyperLoop primitives to build fast replicated storage transactional systems. We implemented HyperLoop primitives in a C API library. We implement operation forwarding scheme by modifying a part of user space verbs library, RDMA verbs library, and NIC driver. As case studies, we integrate HyperLoop into two in-memory databases, RocksDB and MongoDB. Since RocksDB does not natively support replication, we can add replication functionality by using HyperLoop by modifying 120 lines of code. For MongoDB, we replaced the existing replication module with HyperLoop by modifying around 860 lines of code. To evaluate the benefits of HyperLoop, we use a testbed consisting of 8 servers equipped with RDMA-capable NICs. In the evaluation, we assume storage nodes are equipped with a barrier-backed DRAM, which is a form of MVM available today. So we use TempFS file system to emulate MVM on top of DRAM. As a comparison point, we implement the baseline library, which supports the same set of API as a HyperLoop library, but uses CPU to handle operations. We evaluate the performance benefits using micro-benchmark and application benchmark. Using the micro-benchmark, we measure the latency of each primitive while emulating busy CPUs on replicas by introducing some CPU-intensive tasks. This graph shows the tail latency when performing memory writes on a group of replicas. X-axis is the data size and Y-axis is the log-scaled latency. We can see that compared to the baseline, HyperLoop can reduce 99th percentile tail latency by around 800 times. We also observed that the average latency is reduced by around 30 times compared to the baseline. This research demonstrates that offloading memory operations to a group of replicas is beneficial to reduce both average and tail latency. And using the application benchmark, we evaluate the performance benefits for existing in-memory storage applications. I'll show you the results for MongoDB in this talk. As mentioned earlier, we modified the backend part of MongoDB to integrate our baseline and HyperLoop library. Here, the x-axis is the different YCSC workload, and y-axis represent the latency for running each workload. We emulate the case where 10 tenants are co-located. We can see that HyperLoop can reduce tail latency of MongoDB for all workloads. For instance, it reduces tail latency by around 5 times for workload A. We have other results in the paper showing the latency reduction for a while performing memory copy, compare and swap on a group of replicas. Also, we show that HyperLoop can reduce the tail latency for RocksDB by 24 times. To conclude the talk, predictable low latency is lacking in replicated storage systems today. And the root cause was CPU involvement on replicas. To solve this problem, we propose HyperLoop that accelerate transactional operations by offloading them a group of NICs with the support of MVM. And we showed that it can be applied to existing applications with minimal modifications and reduce both average and tail latency. Our work shows the feasibility and benefits of abstracting transactions into memory operations and offloading them to a group of NICs in a context of storage applications. There are lots of opportunities for future works in terms of applying our insight to other data center workloads and applications. and generalizing this approach to utilizing remote memory more efficiently and effectively. With that, I'm happy to take any questions. Thank you.
I think I can get started. So in terms of NVM, I noticed that you use backed DRAM. Intel has been talking about years for NVM availability. What's the latest on that? Are we going to get real NVM sometime in the near future? Micron has also been making noise. I'm just wondering what the sort of story there is.
So actually, I'm not sure about the current status of NVM technology, but at least in Microsoft, some cluster uses very backed NVM, very backed DRAM for like a fast caching storage system. Yeah.
So hello, Danny Chen from Princeton University. Can you provide more detail about the commit phase, especially when one of the commits succeeded and the other commit fails? In this case, what does group commit does?
What are the commits?
So because you do a group commit on all the nodes, and maybe some of them can provide success, some of them can provide fail for you, right? In this case, are you undoing the commit lock and try to do again, or?
Sorry, in which case commit can be failed?
So for group commit, so it could succeed or it could fail. And it failed because maybe some of the nodes fail and some of the nodes succeed. And in that case, what do you do? Are you canceling all the success?
We can undo because we have log, so we can undo the commit.
But then, I mean, if the ordering for commitment from different clients are different, then you could cause starvation, which when two people try to do group commit and then they never succeed, and they will just keep doing group commit with each other, right?
There's only one transaction coordinator which can initiate the commit, group commit.
I see. I see. There's only one. Okay.
That's our framework work.
Thank you.
Hi, Tim Wood from George Washington University. I think you said that you're not using a real SmartNIC yet in your implementation, but I'm curious, how much of the SmartNIC capabilities do you think you would be using for the processing you need here? And are there other things that you could offload to the SmartNIC that might help with this type of application?
Can you repeat once again?
So you're not using a SmartNIC yet, is that correct? So do you have an idea of how much of a SmartNIC's capacity would be required to run to track your commits and things like that here?
Oh, I see. So I think with SmartNIC, we can implement a part of RDMA protocol or part of our idea, the core idea to SmartNIC. So I think it's doable. Also, I'm not sure about what's the overhead will occur in SmartNIC implementation.
Let's thank the speaker again. Our next speaker is Radhika Mittal. Radhika just finished her PhD at UC Berkeley. She'll be spending a year at MIT before starting as faculty at UIUC in fall next year. This is actually her second talk of the day. And in this one, she's going to try to answer the question as to whether we really need network support for RDMA or not. So, over to you.
Thank you for the introduction, Hitesh. So hi, everyone. I'm going to talk about our work on re-examining the network support for deploying RDMA in today's data centers. This work has been done in collaboration with my advisors, Sylvia Ratnasamy and Scott Shankar at UC Berkeley, with Aurojit Panda, who is now at NYU, with Arvind Krishnamurthy at University of Washington, and with Alex Shpiner and Aitan Zahavi from Mellanox. So I'll start with a very quick summary of the problem that we are trying to solve and our findings. So in these last few years, we have seen this new trend where many data centers have started moving away from using the traditional TCP/IP networking stack in the kernel towards using RDMA or remote direct memory access. With RDMA, networking functionalities such as packetization, reliability, and so on are all offloaded to this specialized hardware NIC, but also has direct access to the application memory. And this allows the servers to achieve negligible CPU utilization, ultra-low latency, and high throughput, all of which are highly desirable in today's data centers. And RoCE, or RDMA over Converged Ethernet, has emerged as the canonical means for deploying RDMA over the Ethernet fabric in the data centers. But RoCE needs a lossless network to get good performance. And so the data center network is made lossless by enabling Ethernet's priority flow control, or PFC mechanism, which, as we'll be seeing a bit later, has a number of known issues that a community is now actively trying to resolve. And this has greatly increased the complexity within data center networks. So with this work, we take a step back and we ask, do we really need to deal with that complexity? Do we really need a lossless network to deploy RDMA? We find, of course, that the answer is no, and that by making some incremental changes to the RoCE NIC design, we can actually enable better performance without a lossless network. So with this quick overview, let me dive into more details, starting with some background on the history of RDMA. So RDMA was traditionally designed to be used in InfiniBand clusters, where losses are extremely rare because of the use of credit-based flow control. And as a result, the transport in these RDMA NICs was never designed to deal with packet losses efficiently. The receiver simply discards any out-of-order or out-of-sequence packet, and the sender does a go-back-N loss recovery upon detecting a packet loss. So with go-back-N, suppose packet number X is lost, the sender would retransmit all of the packets that were sent after packet number X. Then when people realized the need for doing RDMA in data centers, they decided to deploy RDMA over the commodity Ethernet fabric. And this led to the introduction of RoCE, or RDMA over Converged Ethernet, that allowed us to run RDMA over the Ethernet fabric. And this was soon followed by RoCE v2 that allowed us to run RDMA over IP routed networks. So in the rest of this talk, I'll be using the term RoCE for both RoCE and RoCE v2. Now, while the network layer was adapted to allow us to run RDMA over IP and Ethernet, the transport layer remained the same as what it was in InfiniBand-based RDMA. So the transport layer was not changed. So the receiver continued to discard out-of-order packets, and the sender continued to do go-back and loss recovery. And because of this inefficient loss recovery mechanism, RoCE NICs needed a lossless network to get good performance. And so the network was made lossless by enabling priority flow control, or PFC. So for those of you not familiar with PFC, it's basically a pushback mechanism where the switches pause their upstream entities from sending more data when the queuing exceeds a certain very carefully configured threshold. And experiences with PFC deployments have shown how it greatly complicates network management, and it also leads to a number of performance issues, such as head-of-the-line blocking or unfairness, where I can have one aggressive flow that triggers pauses that ends up pausing other victim flows. I can have congestion spreading, where pauses in one link can spread throughout the network, pausing the whole data center network. And it can also lead to network deadlocks under certain cases, where switch A pauses B, B pauses C, C pauses A, and no one really makes progress. So given these issues with PFC, in the last couple of years, we have seen multiple papers that are trying to draw the attention of our community towards these problems and proposing fixes for them, which have ended up increasing the complexity of network management. So looking at the state of affairs made us wonder, do we really need to deal with all that? Do we really need to make our network lossless? Or can we instead alter the RoCE NIC design by improving its loss recovery mechanism such that it does not require a lossless network? This very naturally led to the question of, why don't we use IWOP? So IWOP was designed to support RDMA over a fully general network, and it does so by implementing the entire TCP stack in the hardware NIC. So basically, because it implements the entire TCP, it can handle packet losses better. But it also needs a number of translation layers to translate between the RDMA and the TCP semantics. Now, given that these IWOP NICs existed, we wondered why wasn't IWOP adopted more broadly? What led to a wider deployment of RoCE? So we went and we talked to a number of RDMA customers and NIC vendors, asking them what made RoCE the more popular choice. And while we never got a very clear evidence for this, the general consensus among people was that IWOP NICs are more complex, they are more expensive, and that they have worse performance in terms of throughput. So we decided to validate this widespread belief by conducting some experiments of our own. So we had a very simple testbed of two machines connected to one another, and we had IWOP NICs in both machines for one set of experiments, and RoCE NICs in both machines for another, And we ran a very simple write benchmark with 64 bytes messages. So, and we found that IWOP NICs, which also had a slightly higher cost, did result in significantly lower throughput and higher latency. I'd like to point out that this cost and performance differences between IWOP and ROCCI should be taken with a grain of salt because they can arise out of a number of reasons other than just the transport design. There could be differences in the profit margin, the engineering effort, the supported features, and so on. But nonetheless, these results did tell us that our initial conjecture that improving loss recovery could be better than making the network lossless might not entirely be true, at least based on IWOP. Our primary contribution with this work is to show that IWOP did in fact have the right philosophy, that we should allow the NICs to efficiently deal with packet losses, and that can have a better performance than having a lossless network. However, we do not need to have the entire TCP stack in our NICs. We instead identify the incremental changes that we need to make to the ROCCI NIC in order to improve its loss recovery, and this results in a design that is much closer to ROCCI and is therefore significantly less complex than IWOP. We call our new design Improved ROCCI NIC or IRN. With that, at a high level, makes two key changes to ROCCI. And I'll discuss these changes one by one. So the first change that we make is, of course, better loss recovery. Now remember how ROCCI does go back and loss recovery? So just to recap what go back and does, suppose the sender is sending 5 packets, 1, 2, 3, 4, and 5, and say packet number 2 is lost. The receiver now simply discards packets 3, 4, and 5 because they're out of sequence and it was expecting sequence number 2, and it sends a negative acknowledgement telling the sender that I wanted packet number 2. When the sender sees this negative acknowledgement or a NAC, it then retransmits all of the packets that were sent after packet number 2 along with packet number 2, of course. Now you can see how this inefficient form of loss recovery leads to too many redundant retransmissions and therefore wastes time and bandwidth. Now, instead of doing this go back and loss recovery with IRN, we do selective retransmission. So when sender sends packets 1, 2, 3, 4, and 5 and packet number 2 is lost, with IRN, the receiver does not discard the out of order packets and selectively acknowledges them, and the sender only retransmits the lost packet. And we maintain simple bitmaps at both the sender and the receiver to track the lost packets. So the selective retransmission scheme is not very new. It has been inspired from traditional TCP, but our design is much more simpler and it's more tightly integrated with the RDMA semantics in ROCCI. Now, selective acknowledgements can be useful in recovering from packet losses quickly only when there are enough packets in flight to generate these selective acknowledgements. For tail packet losses or for losses in single packet messages, we need to rely on timeouts. And these timeout values can have a huge impact on performance if they're not configured correctly. A very small timeout value can lead to too many spurious retransmissions, and a very large timeout value can result in high tail latency. So, to increase the robustness for how this timeout value is set, with IRN we use 2 timeout values, and RTO low value is used only when there are a small number, n number of packets in flight, and we use a higher RTO high value otherwise. So we set n equal to 3 in our experiments, but we verify that we are not very sensitive to this precise n value. So to recap, this is the first change that we make with IRN, better loss recovery, where we do selective retransmission instead of go back n, and we use 2 timeout values instead of 1. The second change that we make with IRN is what we call BDP-FC or BDP-based flow recovery, where we bound the number of packets in flight by the bandwidth delay product or the BDP of the network. So this BDP is a static value that is computed based on some estimate of the longest propagation delay in the longest path of the network and the link bandwidths. And this again is not something very new. It has been proposed and used in prior schemes before. And it basically helps us in improving performance by reducing unnecessary queuing. And the main advantage it has in our case is that it gives us a strict upper bound on the amount of state that is required to be maintained at the 2 endpoints in order to keep track of the lost packets, because it gives us an upper bound on the total number of out-of-order packets that can be there. And this makes our hardware state management much more tractable. Okay, so these are the 2 changes that we make with IRN, better loss recovery, and BDP-based flow control. Now, the first natural question that we would like to evaluate is whether these changes are enough to actually eliminate the need for a lossless network, which is what our main goal is. So we evaluated that using a simulator that was developed at Mellanox, which models their ConnectX-4 NIC and is extended from Omnet INET. And we extend the simulator to also support IRN. And we model a typical data center scenario with 3-layered factory topology, links with capacity 40 Gbps and delay 2 microseconds. We used a workload comprising of mix of flows with heavy tail distribution, so on. So the first thing that we compared was how Rocky with PFC performs when compared to IRN without PFC. So the graph here shows the average flow completion time, so the smaller is better. And we see that IRN without PFC performs significantly better than Rocky with PFC. Now the differences between these two results here can arise due to multiple reasons. First is IRN's use of BTPFC, which Rocky doesn't use. And the second is the bad effects of using PFC, such as head-of-the-line blocking, congestion spreading, and so on. So in order to distinguish between these two reasons, we next conducted an experiment to see how IRN's performance is impacted when we enable PFC with IRN. Because if doing so significantly improves IRN's performance, we'll have to conclude that PFC remains necessary even with IRN. So we next enabled PFC with IRN, and we saw that enabling PFC continued to degrade performance. So the only difference between the gray and the blue bar here is that with the gray bar, we use PFC, whereas the blue bar uses IRN's loss recovery mechanism. Both of them are doing BTPFC. So what this result tells us is that even though it may take us some time to detect and react to packet losses, doing that can actually be better than enabling PFC and suffering the bad effects of losslessness. Now the next natural question that one might be thinking is, given that PFC performance can be so bad, did it even help to begin with? What would happen if I disable PFC with Rocky as it is implemented today? So we next disabled PFC with Rocky, and we found that disabling PFC significantly degrades performance. This is because of Rocky's use of go back and loss recovery, which has too many redundant retransmissions and therefore increases congestion. So what this result tells us is that the changes made by IRN are important to eliminate the need for a lossless network. So these are our three basic results. IRN without PFC performs better than Rocky with PFC. IRN does not require PFC, whereas Rocky does require PFC. And we find that these key trends hold across different metrics. So here we have average flow completion time. They also hold for tail flow completion times that are dominated by the larger flows in our workload, as well as average slowdown, which is dominated by the shorter flows in the workload. So slowdown here is the completion time of the flow divided by the time it would have taken to complete on an uncongested network. We also tested that our key trends hold even when Rocky or IRN is used in conjunction with other explicit congestion control mechanisms that were designed to mitigate some of the PFC issues. For example, timely and DCQCN. And again, our results hold for average flow completion time, tail flow completion time, and average slowdown. We reran our experiments across a wide range of experimental scenarios, changing the link bandwidth from a default of 40 Gbps to a lower value of 10 Gbps and a higher value of 100 Gbps. We varied the workload to include more uniform workload patterns as well as incast patterns. We increase the scale of the topology, the link utilization levels. We increase and decrease the buffer sizes, and so on. And our key takeaways hold across all of these scenarios. So our results therefore indicate that IRN can indeed eliminate the need for a lossless network. Now the next question that arises is, can IRN be implemented easily enough, or does it have a huge implementation overhead? So I'll now provide a very high-level overview of some of IRN's implementation challenges and overheads, but you can find more details in the paper. So the key difference between IRN and Rocky with respect to implementation is that with IRN, we now need to deal with out-of-order packet arrivals, whereas Rocky can simply discard out-of-order packets. So dealing with out-of-order packets results in some issues that we need to address. And I'll go over them at a very high level. So for some RDMA operations, such as RDMA writes, crucial information is carried in the first packet of the message that tells the receiver how the subsequent packets in the message are to be processed. With IRN, we need to replicate this information across all packets in case the first packet is lost. For some other RDMA operations, such as sends and write with immediates, crucial information is carried in the last packet of the message that tells the receiver how the completion event is to be processed. So with IRN, we store this information at the endpoints until all packets of that message have arrived. Some RDMA operations require some implicit matching between a packet and the corresponding work queue element that generates those packets. And this implicit matching can break because of out-of-order packet delivery. We resolve this in IRN by assigning an explicit sequence number to these work queue elements that the packets can carry. Another change that we need to make with IRN is we need to introduce acknowledgements for RDMA reads, since IRN relies on acknowledgements for loss recovery in BGPFC. So what this basically implies is that we do need some changes to the RDMA packet format in the form of introduction of new packets or header extensions. But these changes are encapsulated within the UDP header that Rocky V2 uses. And in terms of overhead, it adds up to a maximum of 16 bytes per packet. And it could be less than that depending on which operation is being used. We also analyzed the total memory overhead required for maintaining different states needed by IRN, comparing it to the memory supported on a recent RDM-enabled NIC. And we find that our total memory overhead comes out to be only about 3 to 10%. We also synthesized IRN's packet processing logic targeting an FPGA device that is supported as a bump on a wire on Mellanox Nova Flex NIC. And our synthesis results indicate that IRN's packet processing logic consumes only about 4% resources on that device and can support a throughput of 4.45 million packets per second without pipelining, which is more than the maximum throughput we observed on Mellanox ConnectX-4 NIC. So our analysis therefore indicates that IRN can indeed be implemented relatively easily. And I've also had very detailed conversations about IRN's design with commercial NIC vendors. And inspired by results, Mellanox is considering implementing a version of our design in the next release. So to conclude, in this paper, we propose an improved Rocky NIC or IRN that makes some incremental updates to the current Rocky NIC design in order to better handle packet losses. We show that IRN performs better than Rocky without requiring a lossless network, and that the changes required by IRN introduce only minor overheads. Our FPGA synthesis code is available online publicly. And with this, I'm happy to take any questions you may have. Thank you.
Way back from the Microsoft research, very exciting talk. So to the best of my knowledge, I think the Mellanox CX5 and the CX6 can already run the top of the lossy networks. So I'm wondering, what is the difference between your work and the Mellanox CX5 and the 6?
I think Mellanox CX5 can have adaptive routing. Oh, you're talking about resilient Rocky? Or what do you mean by can run over?
I mean,
do they have selective retransmission? I don't think so. I think you're talking about DCQC and support for...
No, I'm not saying this. I'm saying that CX5 and CX6, as they claim, can run on the top of the lossy networks. That ECN is unnecessary.
That what is unnecessary?
So, I mean, what is the relationship between your work and the CX5 and the CX6?
Okay, so I'm not entirely sure about Mellanox ConnectX-6. Aitan is in the audience. You can talk to him later offline. Mellanox ConnectX-5, from what I know, can support out-of-order delivery for some specific operations, not for all. And it does have DCQC and support that can avoid losses to some extent under certain scenarios, but not across all scenarios. So I can pull out some results for, okay, I don't see my backup slides. We have some results in the paper that compare resilient Rocky with selective retransmission. And I think the Mellanox people who developed resilient Rocky would agree with our results, given that they're also an author on this paper.
Okay, thank you very much.
Yeah.
Hi, Uri too with Intel. While I'm not representing my employer here because I'm one of the early designers of iWarp, and I was wondering if you made the comparison at the same speed between those.
Yes, I did.
I think that if we want to compare those technologies, it probably needs to be a little bit more elaborate effort. And I think we need to be careful to separate commercial issues from technical issues.
I completely agree, and I did set the bandwidth to the same both were at 40 Gbps when I compared. And I do agree, I already have that in my slide, that there could be multiple reasons as to why these differences arise. And I do believe that we should try to figure out what those reasons are. And I believe in the iWarp philosophy. Thank you.
Hi, Harold Liu from Alibaba. a great work, I have to say. So because everybody hates PFC and we want to remove it. Yeah. So I have a question about the details. So, for example, for the flow control, you need to estimate the on-fly packets. It's kind of worry me is that what if your estimation is not correct and yeah.
So we don't estimate on-flight packets very precisely. We just use the last acknowledged packet, the last acknowledged sequence number and the sequence number that I'm about to send, and we check the difference and see if it's less than or more than BTP. So, and we don't need a very precise estimate. It's just some heuristic to give a bound on the total number of out-of-order packet without sort of underutilizing the link. So that's the only reason. Even if we are like 2x, 4x off, it does not make a big difference, and we have some results for that in the paper.
Okay, thanks.
Let's thank Radhika again. Our next speaker is Rolf Neugebauer. That was impressive, I had to practice. He's currently an independent researcher. Before that, he was at Docker, and some of the work that he'll describe was actually done when he was at Metronome.
That's correct, yeah.
And in this talk, he'll tell you everything you ever wanted to know about PCIe performance.
Probably a bit more. So this is joint work with my collaborators, which are at a variety of universities. So over the last 10 years or so, we have seen a lot of networking functionality being pushed to the end systems. So particular things like OpenFlow, because it enabled more flexibility. But more recently, we have seen with the rise of programmable NICs and FPGAs that they enable offloads of some of these network functionalities actually into the NIC and NIC customizations. And we actually had a talk earlier in the session about these type of offloads. So people want to, instead of using expensive x86 cores, use the capability of programmable NICs to provide things like isolation between tenants in a network, cross load balancing, and even application-specific processing like the RDMA replica we saw earlier. And this is not just in academia. So at NSDI earlier this year, Microsoft published a paper and they demonstrated that they actually have smart NICs in production today in data centers. So, but if you actually want to implement the offloads yourself as part of research or in production, there are actually quite a lot of potential bottlenecks. And one of the bottlenecks is the PCI Express and the implementation in the host systems. And this is what the rest of the talk is about. So to give you a very brief overview of PCI Express, it's basically the de facto standard for connecting high-performance I/O devices to the rest of your server. So NICs, NVMe, storage devices, graphics cards, TPUs, all these high-performance I/O devices are connected via PCI Express. So the PCI devices are connected to the rest of the system by something called a PCI root complex, which is basically linking PCI with a memory controller and the cores and sometimes the caches. PCI devices then transfer data to and from memory via direct memory access or DMA, and that's typically implemented by DMA engines on the devices themselves. So the host typically doesn't have DMA engines, so all the data transfer is driven by the devices. Since this is a networking conference, PCI is almost like a network protocol. So you have packets, which are called TLPs. You have these packets have headers. There's an MTU, which is called MPS, maximum payload size. There's flow control. There's addressing. There's switching, so you can have PCI switches. And there's even NAT, as we're going to see later in the talk. And being a protocol, or almost like a protocol, PCIe also has some overheads. So if you look at a typical PCI device as you find in 40 gig NICs, at the physical layer you have about 62 gigabits a second bandwidth. If you then look at just wanting to transfer a fixed amount of data, like 256 bytes, and you add up the overheads from flow control, but also the headers which are added to the payload. Depending on the payload, your achievable throughput goes to something between 32 and 50 gigabits a second, and that's a black line in this diagram. And you see sort of a sawtooth pattern here, and that is because of the MTU or MPS. So once you transfer up to like 256 byte, if you then transfer 2566 bytes, you have to send another packet with another header on from, so your throughput drops. Now, if you then actually, this is just for pure data transfer, but if you then actually implement or model something like what a normal NIC does, so you have descriptor rings and host memory, you have queue pointers on the NIC, and all these accesses, like transferring descriptors, are all PCI transactions. So if you model this in a very simple fashion, so you want to transmit a packet, so you put a descriptor on your ring, you ping the device by writing to device register, the device and DMA is a descriptor, DMA is the data, and transmit the data. So if you implement that in a very simplistic fashion, your throughput can actually go down to something like 12 gigabits a second, and that's the blue line, which is labeled simple NIC. And these are all PCI protocol overheads, because every PCI transaction adds a few bytes, up to 20 bytes. So what NIC vendors then do is they obviously start batching things. And the obvious thing to do is you're transferring a group of descriptors, so you have only one PCI transaction rather than many small transactions. You also try to avoid queue pointer updates, etc. And if you do these type of optimizations, you actually get to a performance level, which are the two other lines in the graph, where you can actually get up to 40 gig Ethernet line rate at about 128 byte packets, but not at 64 byte packets. It just doesn't fit over the PCI bus. But what that also means is, now if you implement your offload, you have to deal with batches of descriptors, you have to do caching and buffering on the host, on the device, so it increases the complexity of your implementation on the NIC, and also the driver, because you also want to enqueue batches of packets, etc. So these are just the overheads. But if you look at real implementations, and so here we have taken an Exablaze NIC and modified the firmware on it to look what the contribution of PCI is to the latency of a transaction. So we basically take a timestamp just before the packet gets handed off to the DMA engines, and then compare it on the host. And that allows us on round trip times to calculate, to measure the contribution of PCI Express to the latency. And as you can see in this diagram, the pure PCI contributions to the latency of a round trip packet is actually really high. So it ranges between 90 to 72% of the overall latency. Furthermore, if you look at the absolute numbers, and the graph is not rooted at 0, but it starts at 600. So even for like 200 byte messages, you see the round trip latency to be between 800 and 1,000 nanoseconds. And if you go back to the talk earlier today about the HOMA presentation, where it was about small message latency and the desire to get into single-digit microsecond latencies for messages, now your PCI contributes quite a significant chunk to it. But it also has implications on how you design your NIC. So consider Ethernet line rate at 40 gig and 128 byte packets. So that means a new packet arrives every 30 nanoseconds. But it takes 400 to 500 nanoseconds to transfer to the host. And that means your device and your offload now has to handle about 30 concurrent DMAs in each direction, plus also handle descriptor DMAs. So it's even more complexity if you design your system. But actually it gets a lot worse. So these are just sort of baseline numbers. So what we have done, we've measured the distribution of 64-byte DMA read latencies on two different systems. So so this is a CDF of the two systems. On the x-axis, you see the latency. On the y-axis is the distribution. So on a Xeon E5 system, we measured out of 2 million transactions a median latency of 540 nanoseconds, and the 99th percentile is like 570. So it's a really nice straight line. That's what you like when you design systems. And there are some outliers which go up to like 1 microsecond. The black line, in contrast, is a Xeon E3 system, incidentally of the same generation. So both are Haswells, both are roughly the same core frequency. And here you see that the median is more than twice the median of the Xeon E5 system. So now you have even higher latency, so which means more complexity. But what's worse is that the 99th percentile goes up to like 5 or 6 microseconds. And we have measured, out of the 2 million transactions we've done, we have measured latencies of up to 5.8 milliseconds. So that's several orders of magnitude. As to the reasons why the system behaves so different to the other, although they come from the same vendor, we strongly suggest that the Xeon E5 system is more tuned towards high performance I/O throughput, but also we noticed there's a lot of power management influence on PCI latency and throughput. However, the lesson here is that if you implement offload, you have to understand these latencies and potentially deal with it, or alternatively not use a Xeon E3 system, but stick to E5s. At the same time, we've also seen that the PCI host implementation is evolving a lot. So I showed in the diagram earlier that the PCI root complex sits next to the memory controller and the CPU caches. So Intel actually has done a lot of integration of the PCI root complex with the caches, so you can DMA straight in and out of caches. Also, the PCI root complex is integrated in each socket. So if you have a NUMA system with multiple sockets, now your PCI device accessing memory on a different socket has different access characteristics to memory than you have if you just have a single socket system. Finally, most systems today have an I/O MEMU interposed between PCI devices and the host memory. But what all that means is that the PCI transactions are dependent on both temporal state of the host, the content of caches, but also the location of host memory where you DMA to and from. So I'm going to look at the I/O MMU impact a little bit in more detail. To give you an idea what an I/O MMU does, it's interposed in the data path between the device and the host. And what it does, it translates addresses in PCI transactions. So here's an example where a device tries to DMA read from a particular address. It goes through the I/O MEMU, and the I/O MEMU then will do a lookup in a cache or a TLB to see whether the translation has already been cached, and will use that cached location. And if it's not in the TLB, it will have to do a page table walk because in order to get the destination address. And page table walks are quite expensive because you have to access multiple memory locations, etc. And then you get the host address. The reason you want to have an I/O MEMU in your system is in order to assign PCI devices to virtual machines, and virtual machines don't necessarily know the host physical addresses, and you want to provide protection so that a device assigned to a VM the VM can't program the device to DMA to random memory which belongs to another VM. So you need to have some protection and translation going on. So you can see that there will be a difference between a transaction which hits the TLB and a transaction which requires a page table walk. So how do we measure this? So first of all, we do DMA reads of fixed sizes, so like 64 bytes or 128 bytes, and we do it from a random address on the host, which is pre-registered with the system. And then we systematically change the address range or the window in the host memory which we access. So we start with like 4K, and then all transactions go into the 4K, and then we do grow the region we can access. And then we measure bandwidth and latency, and then we compare the performance we see with the non-IMU case. So here's one of the examples. So what you see here is the comparison of the percentage change of a bandwidth of a PCI read transaction for different regions, different sizes of regions in host memory we are accessing. And it's a percentage change between the non-IOMU and the IOMMU case, right? And you see a very dramatic drop, in particular for small DMAs of like 64 bytes. And you can see that the throughput can drop by up to 70% once you go beyond the size of the TLB and you start having to do page table walks for every DMA. You see that your performance drops by over 70%, right? And the impact is less pronounced for like smaller, for larger DMAs, but even for 128 byte or 256 bytes, it's still like a 30% drop in performance. One interesting side note of this graph is that on this particular system, if you look at where the performance starts to drop, which is at 256K bytes, and we are using 4K pages for the IOMMU here, we can actually determine that the TLB on this particular system has 64 entries, because after that we start thrashing the TLB. And that is actually a number Intel doesn't publish. So, but what this also means that if you design your system and you design, when you allocate host buffers, you want to allocate them together, you want to make sure that you use as little TLB entries as possible. So hopefully these 2-3 samples show you that sort of understanding the PCI performance and the implementation and how it's implemented in the host system is important. It turns out that there are like a plethora of tools to analyze and understand operating system and application performance, but we actually found very little available on PCI Express. There are no performance counters, or there are hardly any performance counters in the chipset, so you really have very little visibility. But at the same time, it's very important, in particular for low latency applications, to understand this impact of the implementation, because if you implement programmable NICs, you have to deal with high data rates. It's not just programmable NICs, though, because there are other high-performance I/O devices like machine learning accelerators. Modern storage adapters have huge bandwidth demands as well, so these results apply equally to these. So the way we gathered all the data and the graphs, and there are a lot more in the paper, is we make available something called which we call PCI Bench, and it's in 2 parts. The first part is a model of PCI Express, which we used to model the protocol overheads in the first graph I showed. And this allows you to very quickly analyze protocol overheads and iterate through designs, for example, different descriptor formats, different interactions with a NIC. So at my previous employer at Metronome, we extensively used it to quickly see what performance we could achieve, for example, for packet capture devices versus a NIC, which have completely different interactions with the host buffers. And secondly, there's a suite of benchmark tools which are more in the spirit of sort of LM Bench and H Bench, so they're micro benchmarking tools. And they allow you to record latency of individual transactions as well as bandwidth of batches of transactions. And the tools allow you to very systematically change like the type of PCI transactions you're doing, PCI reads, PCI writes, the transfer size, offsets in host memory. So sometimes you want to measure like the impact of unaligned DMAs versus aligned DMAs. The address range you're touching in host memory, and of course the location, whether it's on the local node or the remote node. Access patterns are changeable, as well as we can control the state of the host caches. So this provides a really detailed insight into the PCI host implementation, like how the root complex is implemented and integrated, but also how the DMA engines on the device are performing. We actually have 2 independent implementation of this tool. One was implemented on the Metronome NFP 4000 and 6000 cards, And there's another implementation which is available for NetFPGA and the Xilinx evaluation board. And they both consist of a firmware or a logic load for the programmable NIC itself, then a fairly small kernel driver in both cases, and a control program which allows you to execute the benchmarks and the tests and gather the data. In the paper, we discuss what is required to implement this methodology on other devices, so I defer you to that. So in conclusion, I hope I've shown you that the PCI protocol itself adds significant overheads, especially for small transactions, which is important for small message sizes, as we've seen earlier today. The PCI implementations themselves, like in the servers you buy, obviously also have a significant impact on I/O performance. So we've seen that PCI Express itself contributes significantly to the I/O latency. We have seen huge differences between two implementations of even from the same vendor in the same generation of processors. So there's an obvious question and obvious future work, how would an AMD system compare? How do they implement it? Recently there have been there are at least 3 ARM64 server vendors out there, and basically their PCI performance, as far as I know, is not known. So this type of tool will help you understand the implementation. We've also shown that the performance is very dependent on the temporal state or host state, like the TLB, and also the caches, of which we have more details in the paper. So another question is, so all the data we have so far is for a single device in a system. What happens if you have multiple high-performance I/O devices? Is there congestion? How does the system deal with congestion? We haven't done that work yet, but it would be a very interesting data point to see how that performs. So we've introduced this PCI bench. We have like 2 implementation, and we hope it aids the development of custom NICs and other I/O accelerator. And we believe that this is the first detailed study of PCI Express performance, which is publicly available in modern servers. So thank you very much, and I would like to point out that the source code and all the data, including data from 5th generation of Intel processors, is all available at the URLs pointed out here. And I'm happy to take questions. Thank you.
Hi, great work. Ben Al-Muntaziri from Stanford University. I've done a little bit of past work on this, and I absolutely agree that understanding the PCIe performance is super important for low latency. The only thing that I couldn't quite follow is when you're measuring the latency in the PCIe, are you basically measuring only one way of the PCIe, or you're basically involving 4 different PCIe accesses? How did you do the measurement here?
It's a single, so for the latency measurements, PCI reads are relatively easy to measure. So you send a single PCI read transaction to the host, and you wait for the data to come back. So that's a single transaction, a single PCI access, right? PCI writes, we can't really measure the latency directly, because from a device point of view, a PCI write is a posted transaction, so you don't get an acknowledgement back. So we don't know when it finished. So for those, I don't think we have them in the paper, but the data is available here. What we do is we do a PCI write, which is a posted transaction, and then do a PCI read from the same address directly after. And because of the ordering constraints of PCI, we are guaranteed that the write succeeded. So we can't measure the latency of the PCI write, but we can see the relative changes of what happens and compared with the PCI read.
Uri Tsur with Intel, again, not representing my employer, but I would make a few comments, because I think after a talk like that, it's obviously advisable.
Okay.
So no doubt that PCIe is overhead, but like any other piano, you do need to tune it, and you do need to use it correctly. So I'll just point out a few data points. With the data as presented, I think it precludes 100 gig NICs simply for the overhead, while the market has them. It also would preclude low latency even RDMA-based, and this topic here is RDMA-based. The IOMMU as an example, people are using huge pages in order to avoid that. That wasn't mentioned. And then obviously for heavy use of data plane for networking, there are techniques like DPDK that dramatically change those numbers, and there are public numbers that are available. So I would suggest anyone who wants to really do some serious work in this to consult those sources.
Sure. So I think the first point was 100 gig. So I'm not concluding, and we don't conclude that 100 gig is not possible. It was just with this particular PCI configuration, which is a generation 3 with 8 lanes, that is the maximum throughput. So obviously you can go to generation 4 and you can go 16 lanes, and then you get more
16 for those,
and then you get more throughput.
Yeah.
Your
latency,
the latency, so the latency, as we pointed out in the paper, the latency is very much dependent on the implementation of the DMA engines. So we use 2 different cards, and we show in the paper that there are differences between them in latencies, and even if you use the ExaNIC, you see a difference. For the IOMMU, we deliberately, in this particular case, used 4K pages in order to show the effect of what's happening when you start thrashing your TLB, and we actually recommend in the paper to use super pages because it's obvious. So I can't remember what there was a 4th point.
Technologies like DPDK. I think it's important to deliver a balanced message. Nobody would argue that there is no overhead or that it is using
DPDK is a good DPDK is a good example, which we also call out in the paper, of where when you change the driver to what the in-kernel driver does, and it basically reduces the number of device accesses and therefore generates less PCI transactions. You actually have better performance, and it's actually shown in the graph I had earlier. Sorry, I could have gotten into more detail in the talk.
Hello, Luis Pedrosa from EPFL. This is a wonderful talk, and you've actually finally answered questions that have been in the back of my mind for years and explained a whole bunch of outliers that we could never really understand. I have a question about some of the features, in particular the IOMMU, which are designed to protect and offer isolation. But in the verification community, there's a school of thought that you can do away with these things if through static analysis or using safe type languages, you can guarantee that isolation is not necessary. Can you disable these features? And if you do, what does it just look like a TLB hit, or is there some other performance points?
No, you can completely disable. So you actually, on Linux by default, you have to enable the use of the IOMMU. So by default, it's not enabled.
And are there other such features that you can disable?
So I believe, so in terms of correctness and security, I think the IOMMU is the most important part, and you can disable it. I would think it will be very hard to have like formal verification of like full operating systems. I mean, I'm aware of some of the unikernel work, etc., where we could potentially guarantee that this particular VM is not generating any host addresses or any DMA addresses which don't belong to it. So you can, yes, you can disable it. But I think for systems where you actually run multiple VMs which are running arbitrary workloads, you probably still need these features.
And when you do disable them, is it as good as your TLB hits, or is there a different performance point somewhere else?
They should be the same as a TLB hit. So we haven't seen any. So where we don't thrash a TLB, there's very little difference between enabling and disabling the IOMMU.
Thank you so very much.
You're welcome.
Hi, Kashyap Demaraju from TU Berlin. I think I have a quick question. So, does the performance change if you enable SRIOV, or does that affect the PCI bandwidth in any way?
Yeah, so that's the IOMMU. So SRIOV, no, so it's SRIOV is more a feature of the NIC.
Right.
So with SRIOV, you essentially just tag your DMAs with different identifiers.
Right, so there's like some PCI bus routing going on.
Yeah.
Does that have any overhead? Or any idea?
Not as far as I know, because they all go the same path. Okay. But then with SRIOV, you would then hit, and that's one of the things we still need to investigate. You potentially hit different, so depending on how the IOMMU is implemented, you hit different IOMMU page tables, but whether the TLB is shared or not is typically not published. So that is one of the ways you could find out whether the TLB is shared or not by using SIOB.
Thanks.
Okay.
Thank Rolf again. The final speaker in the session is Sean Choi. Sean is a fourth-year PhD student at Stanford doing systems research. And in his talk, he'll tell us about the software switch stack at Facebook and their experiences developing and deploying it. Very cool work. Yeah.
Thank you for the introduction. Okay, hello, my name is Sean Choi, a PhD student from Stanford. Today I'll be talking about our experiment on designing, building, and deploying switch software at a large scale. This work is done in collaboration with the members of the network systems team at Facebook, and the result of our experiment is a switch software called FBOSS. And FBOSS is responsible for running a large portion of Facebook's data center network today. So we first start by why we needed to build the switch software from scratch. To give some context, let me share the scale of the Facebook community. Facebook has 4 representative products, each used by billions of people in the world. In fact, 2.5 billion people in the world use at least one of these products, and these numbers are growing as we speak. Our data center network is also growing at a rapid rate to support such a vast number of users. This figure shows the velocity of the growth. The size of our data center, as measured by the number of FBOSS deployments, has grown around 30 times within a 2-year time frame. Although unfortunately we cannot disclose the exact numbers, I can tell you that it is not in the order of ones or tens of switches. What we can tell you is that we are doing better than 1,000 switches per engineer. So such growth came with growing pains that we needed to overcome. One of the main pain points that we focused on fixing was the issues with extraneous features. Switch software provided by the switch vendors is built to support all of the vendors' users' needs. Thus, it is unlikely that a single user utilizes all of the features in the software. The features we don't need still need us to manage them, resulting in an increased cost of management. Such costs include increased downtime, operational complexity, and security holes. Finally, one must depend on the vendors to add new features to the switch software. In the switch vendor world, new features must be carefully selected and verified to best support their entire user base. Thus, a feature may be prioritized over another feature that is more critical to our operation. In addition, new feature needs to be tested and validated to work with a large range of existing features. Therefore, this resulted in a slow rate of change to our network. To solve some of the issues that I just mentioned, the industry started to move towards building what is called a white box switch. A white box switch is a term for custom switch hardware where the data center owners customize the hardware components that goes in a switch. An example of a white box switch we built at Facebook called Wedge 100 is shown on the right. Secondly, this allows the data center owners to pick the minimal software needed for the specific network in mind. Oftentimes, this means that the data center owners have to add a more powerful CPU to the switch in order to run a more complex software. At Facebook, we wanted to run our existing software services on the switch, which leads us to this last point. Facebook has software infrastructure already in place for monitoring and data analytics, logging, service management, and much more. Each of these services run as a separate entity to help our engineers easily add powerful features to new software. This approach allowed us to minimize repeated work and also increase stability. However, vendors generally do not have full access to these tools. their vanilla switch software lacks the fine-grained integration with this system. Thus, we found ourselves building the integrations anyway. Therefore, these reasons led us to build our own switch software that is leaner, easier to iterate, and that can integrate well with our existing infrastructure. That brought us to start our project called FBOSS, which stands for Facebook Open Switching System. FBOSS is an experiment to discover if we can run switch software in a similar way we run our software services. This is so that we can build, deploy, and test our switch software as if we are running a general software service, which is an area where Facebook has an expertise in. Given that, we designed FBOSS with two main design principles in mind. First principle is what we call a switch as a server principle. As mentioned before, we built Facebook with the mind of building a general software service. This means that we employ continuous integration and stage deployment scheme. We built FBOSS to integrate closely with our existing software services as if we are running any other software service. In addition, Facebook services use various open source software that we obtain from external sources, as well as projects that we built in-house and open sourced. So following the same trend, we designed FBOSS to be open sourced and shared with the community. Second principle is what we call a deploy early and iterate principle. We believe that the key to our success lies in how quickly and correctly we release new features. Therefore, we designed FBOSS so that we can deploy a minimal set of required features and continually make piecewise iterations on building and releasing new features. These two principles drove how we built and deployed FBOSS. To give an insight on which existing software FBOSS interacts with, here's a brief example of existing software infrastructure at Facebook. First is Scuba, a real-time monitoring and data analytics engine presented at VLDB 2013. Second is Gorilla, an in-memory time series database presented at VLDB 2015. And most importantly, last is Robotron, a network management system presented at SIGCOMM 2016. Robotron is responsible for managing network configurations, operations, and sending and receiving monitoring data. Given this, let's go over where FBOSS sits in a larger picture. The main job of FBOSS is to translate protocol states into ASIC states and also implement the low-level protocols. In particular, FBOSS sits between external software such as protocol daemons, network configurators, and monitoring services, and the switch ASIC to translate the required states down to the hardware. I want to note that this architecture is not really novel. This is a standard architecture shared across other switch software such as Open Network Linux or Microsoft Sonic. Let's look at FBOSS in the context of a single switch. FBOSS runs in the x86 microserver within a switch. There are various pieces within a switch software, including software that performs monitoring, routing, and configuration, along with software that controls miscellaneous hardware, which we use OpenBMC for. FBOSS is one of these software, and it consists of an agent, a QSFP service, and a CLI process. One of the workflow of FBOSS, as mentioned in the previous slide, is to take the states, such as the routes, from the routing daemons and translate it into the ASIC states using the switch SDK provided by the switch ASIC vendors. Let's dive deeper into the FBOSS architecture. Each of these pieces are presented with more details in the paper. First of all, switch SDK sits closest to the hardware, providing the interfaces to interact with the hardware. Secondly, within the FBOSS agent, we created a layer called hardware abstraction that contains the hardware-specific implementation. Above the hardware abstraction, we have an interface called hardware switch that provides generic interfaces for controlling the switch hardware. Hardware abstractions provide an implementation of hardware switch. Then using the interfaces provided by the hardware switch, software switch implements the actual switching logic. Then there are components called the state observers, which monitor and manage state changes within the software switch. We will talk about the state management in more detail on the next slide. Then the local config generator and the thrift management interface are used for configuring and managing the switch. Finally, the QSFP service manages the front panel QSFP ports. This concludes a high-level overview of the FBOSS architecture. FBOSS manages states via what is called the copy on write tree. The main idea of this is as follows. We organize the switch states in a hierarchical fashion. Let's assume that one of the ARP entry, in this case ARP subscript j, is updated. Then we create a copy of all of the nodes in the path from the ARP j to the root. Then update the node with the ARP entry and change the parents to point at the newly created nodes. In this case, we can see that the parents of ports, VLAN's children, and routes are updated. The reason for choosing this approach is because it requires no read locks when updating the states, except when we are changing the root. Secondly, it is easier to debug as we have every state transition on hand. Finally, it allows for easier restart as we can replay the state transitions. However, it requires a more complex implementation than a simple memory write. And also, it requires more processing per state update. Now I'll talk about how we test, deploy, and manage FBOSS. To provide a context of why we need extensive testing for switch software, we took a representative month of our operational data and categorized the errors as follows. Note that this categorization is not generic, and it is specific only to our operation. We found that roughly 60% of the outages were due to software. Miscellaneous software issues include simple software bugs, configuration issues, and etc. Microserver reboot is categorized as software related because we found that most reboots were related to FBOSS deployments. And the other 40% of the outages was due to hardware. To reduce as much software-related outages as possible, we performed 3-stage deployment via our own deployment software called FBOSS Deploy. This process is quite similar to how we deploy our general software service. First stage of deployment is called continuous canary. It deploys every commits to 1 to 2 switches for each type of switch that we have in our data center. These switches are actual production switches with different SLAs. For example, these switches, we use the switches that manage traffic to our web servers. This stage is meant to catch bugs related to switch initialization, configuration, and errors that surface pretty quickly. The second stage of deployment is called daily canary. We deploy an entire day's commits to 10 to 20 switches for each type of switch that we have in our data center. This stage is meant to catch slowly surfacing bugs such as memory leaks. Final stage is called stage deployment, where a human operator pushes all the outstanding commits to all of the switches. We perform extensive monitoring to see if there are any bugs. Once we see an outage of more than 0.5% of the switches, the commits are reverted. We perform this final task around once every 2 weeks for stability. Now I'll briefly talk about how FBOSS interacts with our central network management system called Robotron. Robotron acts as a centralized configuration database, a network operation manager, and a monitor. FBOSS integrates nicely with Robotron. For configuration, Robotron generates the configuration data. Then FBOSS's local config generator creates local version of the configuration, activates the latest configuration, and stages old configurations. Robotron can also instruct FBOSS to use other versions of the stage configuration. Finally, Robotron sends and receives device states from FBOSS, and both of these operations are passed through FBOSS's drift interface. Now, I'll talk about our experiences running FBOSS in our data center. On our paper, we shared 3 separate experiences, each with its associated theme. First is the side effect of infrastructure reuse. Second is the side effect from rapid deployment. And the last is our experience on resolving interoperability issues. For this talk, and for the interest of time, I'll only talk about our experiences on the side effect of infrastructure reuse. For others, please refer to our paper. We ran into a problem when importing an external library with different service level agreements. Switch software must be more reliable than most software services, as other services depend on the network to function. Thus, the timing constraints are much more tighter. To make the reboots as fast as possible, our switches have a feature called warm boots. where it allows the switch ASIC to retain its tables and configuration at restart. To account for warm boot, we also implemented a feature called BGP Graceful Restart that restores BGP states after warm boot. We found a new software library that we added for the last commit randomly caused warm boot to take longer than expected, which caused BGP Graceful restarts to time out, which resulted in random network outages. It took a while to debug, and the lessons we learned from this experience is that although we are treating FBOSS as just another software service at Facebook, we should be very careful on blindly including external libraries, as switch software has different SLAs versus a generic software service. So, concluding this talk, we found that to scale our data center network, we needed leaner software with rapid updates. Since Facebook has an expertise in building and deploying generic software service, we started FBOSS 5 years ago as an experiment to see if we can build and deploy switch software as if we're running a generic software service. Our experiences show that the experiment was quite successful. FBOSS is capable of quickly iterating, deploying, and scaling switch software. You can find FBOSS within Facebook's GitHub repo or on the address below. And thank you all for staying through the last talk of the day. And I'm happy to take any questions, and we also have members from the FBOSS team who can answer more longer questions offline. Thank you so much.
Hi, Jeremy Epstein, National Science Foundation. Can you comment on whether having your own custom technology has been more or less secure, and how do you measure the security of your technology as compared to the off-the-shelf technology that it replaced?
As far as the security concerned, I do not have enough expertise to comment on that. So sorry about that.
If there are no other questions, I can try to answer that.
Okay.
So hi, Rob, I'm also on the FBOSS team. It kind of comes, for security, it kind of comes down to what you think your attack vectors are. So if your attack vectors are maybe one of my dependent vendors is compromised, which honestly is a pretty substantial attack vector, then this is definitely easier. Like it has higher security. If you're worried about somebody in your team committing bad code that may expose some security vulnerability, this is less secure because this is open source. But it also has, well, so it's open source meaning that all the code is out there for people to read. There's not huge legions of people like the Linux kernel actually auditing this. So it's kind of, from that perspective, it's the downside of open source without the upside. I'm a big proponent of open source there. From a different security perspective, we can integrate, so all of our server has pretty substantial multi-factor authentication and whatnot, and so we can kind of inherit that for free as opposed to layering something on top of an existing vendor device and asking them to support the thing that we want them to support and not having that happen for a couple of years. So it's net, I think it's a win, but it's not a complete across-the-board win. So the question I got asked was, so I'll keep answering questions all day. If people want to take it offline, is the control plane centralized? And so, Sean, I don't know if you want to answer it.
I mean, as far as the control plane, in this case, we're talking about the routing decisions. We have a centralized BGP daemon that decides the routes. Is that correct, Rob?
Yes, it's almost like when you say the control plane, I almost think it's an anachronistic term. So there's the Robotron piece that you were talking about here, and that is centralized. And then there's BGP traffic engineering, which is some BGP agent somewhere injecting routes, and that's also centralized. But then the enforcement of it, there's actually a BGP agent per box. Yeah. And so that's decentralized.
Yeah, Grace from George Washington University. Nice talk. I'm interested in your copy on write technique. So are you using the RCU technique available in the Linux?
Sorry, can you repeat that question, please?
Yeah, so my question is for your copy on write tree, are you using like available techniques for like RCU? Do you know that in the kernel? Or you implement by yourself?
I believe we're not using any RCU kernel.
Okay, yeah, so I guess the main issue is when you have a lot of updates, the overhead will be increasing. How do you solve that problem?
That's a good question. As far as I know, I don't think we have issues with too many updates on the switch that causes that problem. We haven't seen performance issues with too much writes of the updates.
Yeah, that's right. So basically, you know, what is the source of an update? An update is a configuration change, so that happens at human timescales. It's a port down. It's some sort of route withdrawal, and you know, our update rate is on average much less than 1 per second.
Yeah.
So you know, absolutely, we could be some performance gain by going to what you're suggesting, but it's in practice, it's not at all a bottleneck for us.
Right.
Okay, thank you.
Let's thank Sean and Rob again.
Thank you.
Well, thanks for attending the session. I enjoy the rest of your evening and the boat trip. See you there.